Hello and welcome back to the second submodule in the Design for Test unit. In this submodule we're going to cover memory testing and built-in self-test. First of all, memory testing. You have a variety of memories in any modern chip design. These might be register files, which you saw an example of earlier, SRAMs, and embedded dynamic memories. In all cases they're organized, conceptually at least, like the register file example that we gave earlier. That is, we store one word per row of the memory, and we have multiple lines in the memory, and we'll read or write one line per memory cycle. Memories are exhaustively tested. That is, we identify all the potential fault patterns that we want to test for, and we develop a test pattern that tests each and every cell in that memory for that particular fault. However, memories are also very densely packed, in terms of the layout in particular. So we often want to test for things besides individual node, stuck at zeros, and stuck at ones. The most likely additional test is to test for shorts between neighboring locations within the same row and to the row above and the row below. Once we've identified all the fault patterns, all the faults that we want to detect, we create a set of marching test patterns for the memory. That is, they're written to each and every row and they're read out again in each and every row. That way they're considered to march through the memory as we access it one row at a time. So to do this, we typically isolate the memory with scan registers, and quite often a memory test controller that's specifically designed to help support marching in these particular test patterns. So we don't need support from the external ATE equipment, except in terms of initiating and ending the test. So here's a simple example down the bottom here. Here we have 4 patterns that are marched into the memory. We first of all write ones to every location and then read. This is to detect stuck at zeros. We then write zeros to every location and then read each and every location. This is to detect stuck at ones. We then write in an alternating pattern, a checkerboard pattern of 1 0 in say the even rows and 0 1 in say the odd rows, and then read those out. This detects shorts between neighboring cells. We then write in the reverse pattern, say 0 1 in the even rows and 1 0 in the odd rows, alternating the pattern in step 3, that is alternating the checks on the checkerboard, and then read those out to see if they're correct. Quite often there are additional test steps to detect additional types of faults, such as bit line faults, but we're not going to cover these in this particular notes. So that's generally how memories are tested, and again, quite often there's a test controller attached to each particular memory in order to do this testing. In the rest of this section, we're going to deal with built-in self-test. This is conceptually a very attractive feature. Tell the chip, go forth and test thyself, and just tell me if you're good or not. If we could do that with a very low area overhead, it is very attractive. It saves all that headache of designing, of inserting scan chains and the toolpath, working out where the scans are going, where they're not going, and generating all those vectors and compressing those vectors using expensive CAD tools, then applying those vectors using expensive test equipment. This is very attractive, but it has one big drawback. That is, it takes more silicon area than traditional scan-based testing. Thus, it costs more because each and every chip is significantly larger than with just scan-based testing. The basic idea is fairly simple. That is, if we're going to test on chip, we can run at the full clock rate, and we might as well just generate a pseudo-random sequence that, if we run it long enough, has a very high fault coverage. That is, covers a very large, that is, detects a very large number of the stuck at 0 and stuck at 1 faults. So we just run this pseudo-random sequence long enough to get 99% fault coverage, and then we're done. And we can do this at the full clock rate of the chip, and we don't need all that memory and that test equipment to store vectors and store the anticipated results. There is automatic CAD support available for built-in self-test, But again, because the area overhead tends to be larger than scan-based testing, it is relatively rare to use it. There's one big exception, and that is in mission-critical equipment. In such equipment, often it goes through a self-test cycle on each and every power-up, and BIST is very useful for applying that self-test cycle. The way in which the pseudo-random test vectors are generated is using a good old friend from the Verilog 2 module, the linear feedback shift register, i.e. with these XOR gates to produce a pseudo-random number sequence. So the basic idea is for each circuit under test, each combinational logic block, CUT stands for circuit under test, we have an LFSR that is generating a pseudo-random sequence. And it's run long enough to through some CAD tool calculation to get a 99% fault coverage. On the right-hand side, we also have a linear feedback shift register, but slightly differently configured. Is configured as a multiple input signature register, or MISR. An example is shown at the bottom. The MISR is also an LFSR, but with an additional input convolved with the LFSR number. The M's here come from the circuit under test. These are the outputs of the combinational logic of the circuit being tested. They are XOR'd in with the LFSR sequence. The idea is that we get a very unique signature coming out of this at the end of the n clock cycles for which we run this, if the design is fault free. If there's any one fault and any small number of faults in the circuit under test, the signature will be different. How do we detect that it's different from expected? By comparing it in some test controller on the chip where we stored the expected signatures. So by applying this sequence to every combinational logic block, we can test for all stuck at 0 and stuck at 1 faults, or at least a very high percentage of them, in a reasonable amount of time with fairly simple equipment in terms of the external support. Now you might recognize that on this previous diagram we have one circuit under test. In practice, there's an additional circuit under test there, an additional circuit under test there. Thus, the registers in between has to be an LFSR to test the circuit to the right, or it has to be configured as an MISR to test the circuit to analyze the signature of the circuit to the left. It has to be able to do both. For this reason, people have identified and designed this what's called a built-in logic block observer. That is, it can run either as an LFSR or an MISR. This abbreviation comes out to Bilbo, and yes, it is inspired by Lord of the Rings. At the time that these techniques were being developed in the late 1970s, the book trilogy Lord of the Rings was having a resurgence in popularity. And so yes, this particular circuit designer / logic designer who invented these techniques called it Bilbo. The structure of a Bilbo register is shown at the bottom here. The outs at the top are from our combinational logic. C1 and C2 are control lines. Our scan input is not just the scan in from the register to the left, it's also an input from the LFSR. If C1 and C2 are set to 0, the normal scan chain operates. If C1 and C2 are set to 0, 1, then it operates as an LFSR through these XOR gates. If it's set to 1, 0, the LFSR is convolved with these inputs from the combinational logic block out to produce a signature. If C1 and C2 are 1, 1, then simply out is presented to the D inputs of the flip-flop. You can verify this logic for yourself in the circuit above. So the idea is the Bilbos are the intermediate registers, in a chain of register combinational logic block combinations. And at the ends of these chains of register logic block combinations, we have an LFSR at the input and an MISR at the final output. This might be, for example, an interface to a memory above and below, or the primary inputs and outputs of the chip. So the idea is run with the test sequence in 2 stages. Stage 1, we set up the Bilbo to be an MISR, and we test combinational logic block 1 in a pseudo-random sequence. In stage 2, we set up the Bilbo to be an LFSR, and we test combinational logic 2 with a pseudo-random sequence coming from the Bilbo register. And in this fashion, we complete the pseudo-random testing of all the logic blocks on the chip. There are additional complexities here. For example, if you have feedback within the chain of logic and registers and so on, but we won't cover those. They're just complicating details that, again, the CAD tools that support this can actually deal with. Finally, I do want to cover a little bit about how design for test is done in the Synopsys environment. Remember I said it's up to you, the designer, to anticipate the test features will have to added to the chip. And for general logic, you actually need to account for those test features in terms of their impact on the delay of the critical paths. Thus, in general, though I don't require it in this class, in general, you have to run at least some part of the test insertion scripts within your synthesis runs. So here I'm just illustrating what those might look like. Here, for example, I have the additional command, set test methodology full scan. Another alternative would be partial scan, in which case the tools work out which flip-flops can be skipped in the partial scan schema. But here we're inserting full scan. That is, each and every flip-flop in the design, potentially though, including those inside or outside registers you might want to configure as well, register files, is included in the design. So here, each and every register that's in the general combinational logic blocks will be included in the design. We set the style of the full scan register, multiplex flip-flop. We then do a simple compile so that it actually uses these scan registers. Then we have insert test and check test. That's actually checks for testability analysis of the chip. There's unlikely to be any problems that come up here unless you have some very unusual circuitry, but this is done. Now, as a design engineer, you're not necessarily creating a full test pattern, but you want to check that what you've done works, so we create some sample test patterns. Another thing the design engineer has to consider is how many scan chains are going to be supported. Each scan chain has to connect to its own set of pins. So the more scan chains you have, the more pins at least have to be dedicated to or multiplexed for test support. But also, the more scan chains you have, the less time it will take to test the chip. So there is a trade-off here. Much will be dictated by a specialized test engineer, but you as the designer need to know how many scan chains are running through your design. So here we're actually inserting the scan chains, that is connecting up the scannable flip-flops. And again, here we're creating a small set of patterns just to verify that we can actually apply patterns to what we've done here. For full test insertion, it's being done by the test engineer, or possibly in some companies by the designer. After design is complete, after the logic synthesis is complete, you would then go in and generate a full set of test patterns with full compaction, and they'll go into a separate file. They'll eventually be loaded into the test equipment. Here's some advanced topics in tests that we've only covered in shallow detail. Memory test is actually more complex than I've indicated. There are sometimes a dozen or so fault models that are considered in the memory test sequence. Only considered 3, stuck at 0, stuck at 1, and short between neighbors. They're the 3 most important ones. Hierarchical testing. As chips grow larger and larger and larger, we can't test the entire chip in one single pass, so we work out techniques to test it a chunk at a time. and these are used in very complex, large system on a chips. SoC stands for system on a chip. Test compression. There's been a lot of advances in this area in the last few years. That is how to produce the minimal set of test vectors that maximizes the fault coverage. And there's often separate tools that run for this besides those embedded in synthesis. We do not talk much about debug. These DFT features can be useful in debugging a chip. For example, using the scan registers to get the chip into a specific state that's then clocked for a few cycles in order to determine what's going wrong in the states after that. This is a very common practice. The design engineer is often involved in this. And sometimes there's additional features put in to support debug, but these are usually analog light features like noise detectors. I did not talk about boundary scan. That is, the chip I/O themselves are connected to the external world via scannable flip-flop chain. Purpose of this is to be able to test the connections between the chips using these boundary scan registers. Also did not talk about the standards. For example, IEEE 1149 JTAG, which is largely to do with boundary scan. IEEE 1500 to do with hierarchical testing and so on. The idea of these standards is that if you apply these standards to generate your test vectors, you generate them in a format that fits in with a standard set of controllers, which in turn fit in with standardized test equipment. So you can mix and match your choice of test equipment vendors and your choice of test CAD tools and actually be able to run it all without having to rewrite a whole bunch of code or recast a whole bunch of test fixtures. So that ends this particular submodule. Again, the main points. Memory testing is, since memories are dense, we often have more complex fault models than just simply stuck at 0 and stuck at 1. For example, crosstalk models that detect shorts between neighboring cells. This leads to specific test patterns that are read and write exhaustively to the memory. Self-test is commonly used enough to discuss it here. The basic idea is you configure the flip-flops to be LFSRs as well as scan chains. You then use those to generate pseudo-random test pattern sequences that if you run them long enough can provide a pretty complete test, and also use them to generate signatures of the outputs of the test. If you get an incorrect signature, that means you have a fault. Well, that ends this section on design for test. Again, for the section overall, the big thing is that the design engineer has to be aware that design for test is important and it costs chip area and part of the critical path, part of the delays between registers in order to support it. Thus, you'll be expected to input some of the design features for design for test during your design and synthesis runs. Thank you very much for your attention.